Connor, you're a big fan of bacteria. Should we talk about the one that most people know and do not love? Staphylococcus?
The famous cause of staph infections. Yes, why not?
Yeah, these bacteria are not to be messed with, but some good things have come from understanding it, such as, drumroll please,
Oh, how exciting.
the discovery of protein A.
Aha, protein A. Finally an episode on protein A, discovered in our lifetime and is going to drive just the most incredible things for generations to come. So is that what matters on today's episode?
In fact, it is. Let's find out about protein A.
Okay, so what do I need to know about protein A?
Well, we do like a history lesson here on Discovery Matters, so put the jukebox on, slick back your hair as if you had any.
Yeah, what hair?
And imagine that we are back in 1958. We're at the Institute of General Pathology at the University of Copenhagen, and Professor Claus Jensen is exploring cell walls.
Jensen first observed the binding of protein A to serum antibodies. And it's interesting, they speculated the body has natural antibodies against staphylococci. They demonstrated that 100% of healthy subjects had binding to this antigen A. And he speculated that it was due to transmission, passive transmission of antibodies from the mother to children.
Okay, there was a whole load of information there. How are we going to
Don't
work
worry.
this out?
Yeah, we are going to break this down together.
As we would expect. So who are we talking to?
Hi, my name is Glen Bolton. I work at Amgen. I'm located in Cambridge, Massachusetts. I've been in purification development for about 20 years.
Okay, so Glenn basically said that Claus Jensen discovers something, but he's not exactly sure about what he's actually discovered.
That's right. It's just the kind of story we love to retell here on Discovery Matters.
It sounds very, very familiar, doesn't it? And Jensen, or Jensen, it sounds very Scandinavian. Is everything that we do coming back to Scandinavia?
Ja, visst.
Oh.
Scandinavians, in fact, do play a big part in this story, like many others. A few years later, in 1962, another set of Scandinavian researchers, Löfqvist and Sjöqvist, say that 3 times fast, Löfqvist and Sjöqvist.
All the quists.
Yes, in Bergen, Norway. They kind of finish off what Jensen had started, and they confirmed that antigen A was in fact a surface protein on the bacterial wall of certain strains of this Staphylococcus aureus bacteria.
Then 2 years later, they named it protein A after aureus.
Aha, I recognize that voice. Let's meet her.
So my name is Josefin Bolik, and I work as a global product manager. I'm responsible for the next generation chromatography protein A resins.
So it wasn't until 1978 when somebody decided this could make a good purification product.
So that's where it all started for how we utilize protein A today.
So let's break down everything to do with protein A.
Please, let's do.
The protein A's function for Staph aureus is actually to interrupt your immune systems.
Now that voice sounds familiar as well.
Yep, that is our former colleague Jonathan Royce. He loves protein A. I mean, loves protein A.
Protein A sits on the surface of this bacteria, and when your body produces antibodies to try to kill the bacteria, protein A actually binds those antibodies. It actually flips them upside down so that the important part of your immune response can't actually reach the bacterial wall of the bacteria. I think it's really interesting because it is one of these, maybe not accidental discoveries, but it's something that, we have discovered in nature and then found a way to apply it in a very industrial setting. And I think it's also really interesting that in the beginning, no one thought this technology would ever be used at the industrial scale. I mean, it was a lab scale product at the beginning. And if you read some of the first product managers' notes, which are like on typed paper, they were forecasting, maybe someday we'll sell like a liter of protein A. And today, GE and other companies produce tens of thousands of liters of this product. It's a fascinating story from both of those angles, I think.
It is a very interesting molecule, as Jonathan said. It's based as 3 alpha helixes. That structure makes it very good. The amino acids are pretty much protected. So when you actually treat it with, for example, alkaline solutions and so on, it can actually protect the amino acids a little bit. As compared to other protein scaffolds, which are perhaps having more beta sheets, like protein G, those amino acids are more exposed to treatments. So it is a very interesting molecule can you actually engineer it to bind to other proteins as well? Because it has a very good structure in that sense.
It's also quite beautiful. It's quite a striking structure when you see it, these 3 triple helixes and the way that they're intertwined with one another. It's quite unique in the way it looks, and it looks really nice when you see the 3D structure in like a color image. So that's also a reason to love Protein A.
So it's like the kind of natural antidote in our immune system.
Exactly.
Okay, so this is a lot of information. Is it then like flipping a pancake and not cooking the other side? It's the casing on a Kinder Egg. I'm looking for a metaphor here. Help me out.
If you put all your clothes in the washing machine, like a lot of synthetic material and one piece of wool, and you wanted to grab just that piece of wool, you could put the rough side of a piece of Velcro in as well. And the Velcro would only stick to the wool. It wouldn't stick to any of your like training clothes. And that's how Protein A works. It only grabs that thing that you want, and it doesn't grab anything else.
So that's Protein A. It only grabs the thing you want and leaves everything else alone.
So let's backtrack a little bit and tell people listening a little bit more about monoclonal antibodies, or MABs, because that's what we call them in our industry. We call them MABs. They're proteins, antibodies made by identical cloned immune cells, which is why monoclonal, right? So identical cloned cells. And they bind to specific proteins on cells that are involved in disease pathways, like cancer and immune diseases and so on. And they've really heralded a complete revolution in treatments for all sorts of diseases, from cancer to rheumatoid arthritis and so on. And many of today's top-selling drugs are actually monoclonal antibodies, or MABs. And Protein A, it turns out, is just incredibly important in the manufacturing of these drugs on an industrial scale.
Yeah, so this natural specificity to IgGs, immunoglobulins, is very good because you can get rid of all the animal-derived nutrients that is in your cell feed, basically. So it only binds your target, so your drug in this case, which is your monoclonal antibody. So you get rid of everything else. And that has the benefit that the subsequent step, you can actually reduce those. So it has a very good advantage because it's very specific. You get very high purity at the end.
So there is this particular constant part that Protein A is binding to, and Protein A wants to do this.
If you have that on a chromatography resin, for instance, then you bind your drug to the Protein A, which is on the resin, and everything else from your cell culture feed, all the proteins, nutrients, everything goes through the flow through, and you get rid of that basically, and that gives the very high purity of your final drug product.
So what's the future then? How can something this efficient get any better? Or is there a risk of disruption by another technology or another protein?
Protein A has been engineered over the years, ever since that first resin came out. And we've made it more alkaline stable so that it can actually handle, because since you have all those nutrients in your samples, this step is also prone to bioburden incidents. So by cleaning it more harsh, then you can actually get rid of that problem. So we have engineered over the years to actually be able to have those clean in place to higher concentration of sodium hydroxide. But I think going forward, Protein A, now it has been utilized on chromatography beads, but I think it's a protein. It can easily be attached to other new technologies like membrane technologies or fiber technologies. So I think that's what we're going to see going forward.
So here's what that means for drug making.
You still have that specificity, of course, and you can reduce the bioburden incident complications, but also by putting it onto other technologies, you can actually improve the productivity of your process even more. You can run even faster. Over the years, it has been a lot of focus on the beads and to make them more better pressure flow properties and so on, to run the processes faster and also to respond to the increased titers. Now, customers want to have even more productivity, and that's where we're going to see those new technologies come in place. But I think Protein A is still going to be very useful in those new technologies as well.
Protein A columns are the weakest link in downstream purification with respect to the bioburden risk. And so Josefin is going to explain that.
There are all sorts of bacteria that can actually infect your process, basically, because although these MABs are produced in CHO cells, and you can have risks of these bacteria infecting your feed, basically. So that is what we mean with a bioburden incident. And this is very critical to the companies. They have to be in control over this and to be able to show that they can actually reduce those in a very efficient way.
So when Josefin's talking about increasing speed, what are we talking about exactly? Are we talking about like from hours to minutes or months to hours? How much speed?
We typically call it grams per hours in terms of productivity, grams per liter per hours. If it's a resin, that you can actually produce more grams per hour, basically. So that is what we increase or improve.
Okay, so she mentioned cancer. When we see how much cell and gene therapy is evolving in the race to cure cancer, how then do monoclonal antibodies compete with them?
Well, I think both technologies are here to stay, but there are actually interesting, very recent data that was presented by two companies late last year that bispecific antibodies are actually outperforming CAR-T treatments. So that is a very interesting thing going forward to look out for. So I think definitely that antibodies can still have their space when it comes to cancer treatments and so on.
For Glen, he says that if you imagine Protein A as a car, it's like your old Faithful. It's the car that you drive every day, not the Sunday convertible.
Yeah, I think that's a good analogy. You want reliable, economical transportation that you don't have to worry about getting to point A to point B. And then it's sort of a reliable economic transportation for us to get early stage drugs to the clinic and to commercialization for patients.
And he carries on saying that it really is a lifesaver.
It's something that I value a lot because we have to get these drugs out fast. We have to meet the clinical timelines. We have to get them to patients quickly. I don't have a lot of time to spend developing the conditions. I want to get the material through with very little risk. I don't want to lose yield. I don't want to give something that's too impure. So to me, Protein A is kind of a lifesaver in that I can very quickly produce these drugs and move them along to the patients with very little development effort and with good confidence. I'm going to get high yield and high purity. So for me, that's key. I don't have to worry about whether it's going to work. Am I going to lose all my product? Is my product going to be too impure when we're doing early stages of development and we want to rapidly get material out?
So, from something scary and unknown and unexpected, we've found something that's provided enormous benefit to the biotech industry and to patients all around the world.
Exactly. And it's another discovery in an unexpected place. And it's another story for you to use, Conor, when you talk about your love of bacteria.
I love those little guys. Yeah. And my love for ratings for our podcast. So please do that. And thank you for listening.
Catch us anywhere you listen to podcasts, on Spotify, on Apple Podcasts, on Stitcher, on Himalaya. So our listeners in Asia, you find us there.